there's something called an electron configuration, which is very similar to an orbital diagram, which was what the quiz was about. The electron configuration is just giving you a little bit less detail. Right? So this is my orbital diagram. It includes the boxes and the arrows so I can see exactly which orbital all the electrons are in. The electron configuration is a little bit different. It's just a way of showing what subshells the electrons are in. So if I have a hydrogen, which would be the most simplest, straightforward example, I've got one electron. So the orbital diagram shows that one electron as an arrow. The spin could be plus 1/2 or minus 1/2. Right? There's no rule that says a plus 1/2 spin is more stable than a minus 1/2 spin. So I could also have, instead of put it like that, I could have put it like that. As long as it's in that first energy level, that's the ground state. I could also make it excited if I took it out and put it in one of the other energy levels, right? So we have an understanding of what makes ground versus excited versus impossible. So most of what we'll be talking about today are how to come up with the ground state, because that's usually how the atoms exist. Usually they're in their most stable state. So as far as the electron configuration is concerned, though, that it looks like this. So these two are showing the same thing. This just gives me more information. It indicates the spin I'm dealing with in the orbital diagram. In the electron configuration, it's just saying I have one electron in the 1s orbital. Right? It just tells me how many electrons, that's the superscript, and what subshell those electrons are in. Right? So as I go to put more electrons in, now I've got, well, before we talk about that, an excited state, the electron has to be in a different energy level. And again, if I excite it, one way to recognize an excited state is to look for a gap. There's a gap in an energy level that's close to the nucleus, but there's electrons above that gap. That's going to be an excited state, because if there's a gap, they have the potential to move back down. They're at a higher potential energy or an excited state if they have the potential to move back down and fill in that gap wherever the gap might be closer to the nucleus. So here's one possible excited state electron configuration for hydrogen. Right? So normally hydrogen is a 1s1, but if I move the electron to the 2s, then it would be a 2s1. Right? So just again showing the number of electrons, one electron in the 2s subshell.
So you wouldn't actually write the 1s because there's nothing in it?
You could write 1s0 if you wanted. That would be the same as leaving it out. If you don't write it, you would assume there's nothing in it. That's a good question. So when we get to more complex atoms, any atom other than hydrogen with more than one electron, it's going to get more complex. So if you recall these line spectra, what are the line spectra the result of? Right, relaxation, or the electron relaxing. So when I take the electron from the 1s, the ground state, and excite it up, to get these four bands in the colored region for hydrogen, that was the Balmer series. The colored emission occurs when I have an electron that's higher than energy level 2, and it relaxes down to 2. Right? If it relaxes from a higher energy level down to 1, that's a big energy difference. That's not going to be in the visible part of the spectrum between 400 and 700 nanometers. So with helium, what we see is there's more combinations. There's more combinations that are in that visible spectrum. And that suggests that the energy levels are more divided. There's sub-levels that are divided in energy, right? Because I can go from, like, if I'm in the 4th energy level, I could go from the 4s to the 2s, or I can go from the 4s maybe to the 2p. If those are slightly different energy jumps, then I'll see more than one color represented from each one of those possible relaxations. So with helium, there are more possible relaxations than there are with hydrogen, and that tells us that with a atom that has more than one electron, there's a separation in energy between different subshells on the 2nd energy level. There's a separation in energy between different subshells in higher energy levels. So if I do have an electron and I excite it up, maybe to the 5s, there are a lot of different ways you could relax. You could relax from the 5s to the 4p, or from the 5s to the 3d, or from the 5s to the 4s, or a 5s, etc. Right? There's a lot of different combinations. And so each one of those relaxations, if I excite the electron up, each one of those possibilities will release some light with a certain color. And so I get a much more complex line spectra when I have more complex atoms. But I'm still getting a line spectra, not a continuous spectra, because the electron has to be at one of these energy values. It can't be in between them, right? We know that's still quantized. There's still only certain energies that that electron can have, because when it's in a certain subshell, it has a certain average distance from the nucleus that defines its potential energy based on the electron density's attraction to the nucleus. So when I have more electrons to put in, I have to follow the Pauli exclusion principle, the Aufbau principle, etc. So the Pauli exclusion principle, this one is the one that tells us what is possible versus impossible. It says that I can't put two electrons in the same orbital with the same spin. Because if two electrons were in the same orbital with the same spin, they would have all four quantum numbers equal to one another. Right? So if I put two electrons in the same orbital, let's say I put two electrons here, and this is with the same spin. If they're in the 2p, n equals 2, L equals 1 for any p orbital. If they're in the same orbital, then they have the same value for ml. So that might be -1, 0, or 1. But if they're in the same orbital, they have the same value. And if they have the same spin, then they have the same value for ms. So this is impossible. It's impossible for two electrons to have all four quantum numbers the same for both electrons if they're in the same atom. And so that's what you guys understand from the quiz. I know that you understand that. So we wouldn't draw that unless the question specifically said draw an orbital diagram for an impossible atom. So we have to follow that principle. So if I have multiple electrons to put in, and I'm going to put them in the same energy level or in the same orbital, I have to give them opposite spins if they're in the same orbital. So that would be helium in its ground state with 2 electrons. And if I'm going to put both electrons in the first energy level, because there is space for them to be there, it's going to be a 1s2, right? So now I have 2 electrons in the 1s instead of 1. Right. Pretty straightforward. Nothing really unusual about that. So this just shows what the quantum numbers would be. So for the electron that's red, the one with the spin up, if it's in the first energy level, n should be 1. What should the value for L be if it's in the 1s? 0, because it's in an s. And then ms should be 0. So if L is 0, I'm sorry, I meant to say ml. If L is 0, ml must also be 0, right? Because in an s, there's only one orbital, and its ml quantum number would be 0. And then that would have the +1 half spin. So if I'm going to put another electron in the same orbital, the first 3 quantum numbers can be the same, but the last one has to be different. So that would be helium. So then if we continue on, the Aufbau principle says that generally electrons should be in lower energy orbitals before they go to higher energy orbitals. Right? So this is a guideline. The last one, the Pauli exclusion principle, tells us what's possible versus impossible. This tells me what's ground state versus excited. Right, so we can't violate the Pauli exclusion principle. We can violate the Aufbau principle. We just need a little energy to move an electron away from the nucleus from where it would normally be. So if I want to make a ground state for lithium, if it were neutral, would have 3 electrons. So I put the first 2 in there, and then I put the next one in the second energy level, right? I'm not filling any higher levels, because this principle says if I want to show the ground state where the atom normally exists, because of the attraction to the nucleus, the electrons want to go into energy levels and orbitals that are as close to the nucleus as possible. So then the electron configuration would be 1s2, 2s1. Right there. So just showing, if I know I have 3 total electrons, I have to show where all 3 electrons are. 2 of them are in the 1s, 1 is in the 2. This is a much easier way of showing what I've shown here. It just doesn't give me quite as much detail because I don't see the electron spin. I don't see the energy difference between 1s and 2s. So then continuing, if I have 4 electrons, do it the same way. Again, since 2s and 2p are not the same energy, I want to fill this lower energy orbital first. Once I have orbitals that are equal in energy, then I don't want to necessarily fill them up. I want to spread the electrons out to avoid repulsion, right? So why is the 2s lower in energy than the 2p? On average, the electrons are closer to the nucleus because the 2s is more spherically shaped. It has an average electron density closer to the nucleus than the 2p, which is the double lobe, more elongated shape. So that would be the electron configuration for beryllium, 4 total electrons. If I want to go to 5 electrons, now I have to put 1 into the 2p. Does it matter which of the 3 2p I put it in? No. Does it matter whether I draw it as an up arrow or down arrow? No. Because there's no difference in energy between the 2px, 2py, and 2pz, and there's no difference in energy between spinning up and spinning down. So don't get caught up. If I take this electron out and put it in the second middle orbital pointing down, it's still a ground state. Right? It's not an excited state unless I were to move it from the 2p up to the 3s or something like that. Right? So I'm still following the principles, drawing a ground state, and then the electron configuration now would show that there's 1 electron in the 2p. Continuing. Once I put 2 electrons, though, then I follow Hund's rule. Like the last rule, this is about ground state versus excited. Right, as we said, there's only one thing we have to worry about when it comes to possible versus impossible, and that's the putting 2 electrons in the same orbital with the same spin. We can never do that. That's impossible. Any other combination could be possible. So then it's just a matter of, is it a ground state or excited state? So Hund's rule helps us to draw ground states if we follow it. So if I have carbon with 6 electrons, I double them up with opposite spins, and then when I go to the next energy level, if I have multiple orbitals that are all degenerate or equal in energy, I want to spread them out. I don't want to put them next to one another where they repel. I want to spread them out to avoid repulsion. And experimentally, we see that they have the same spin, not opposite spins. How do we know that? I mean, hypothetically, is there any reason why you can think of that it wouldn't be okay to do this? I can't think of any reason. And there's no reason. To me, it seems like this would be more stable. Because if one is spinning up, that creates a little bit of a magnetic field in one direction, the other creates another magnetic field in the opposite direction. That should cause a little bit of a magnetic attraction like it does if they're in the same orbital, right? We already said when they get in the same orbital, they have opposite spins because that helps them attract a little bit to overcome the repulsion of their negative charge repulsion because they get close together. So I would have predicted that they should have opposite spins. If it were true, though, that they had opposite spins, what could I say about the magnetic properties of that element? So excited versus ground state has to do with the potential energy. That's separate from the magnetic properties of the atom. So if we want to make a thought experiment and say, let's say we didn't have Hund's rule. We didn't know whether it was ground state to put the electrons with opposite spins or whether it was ground state to have the electrons with the same spin. We're just predicting, trying to make a hypothesis of which might be more stable. It would be difficult to necessarily say which is more stable. I mean, you can make a logical argument and say it makes sense to spread them out in 2 different orbitals rather than put them together, right? Because if I put them in the same space, they're going to start having a negative charge repulsion. So it makes sense to spread them out. The question, though, is when I spread them out, how do I know that they should have the same spin? Well, I can test that hypothesis experimentally pretty easily. Because if they have the same spin, they're both spinning in the same direction, they're both creating a magnetic field in the same direction. So that would give me an element with magnetic properties, a magnetic element. If they had opposite spins, then the one electron's magnetic field would be canceled out by the other electron's magnetic field going in the opposite direction. They wouldn't have any magnetic properties. Right? So looking at the magnetic properties of different elements allows us to recognize that somehow this element has to be somewhat magnetic. Because if they had opposite spins, it wouldn't be magnetic at all. But when we look at the element's actual behavior in real life, we see that it has some magnetic properties. So we know somehow these electrons have to be creating a magnetic field that's not canceling out. And so if we follow Hund's rule, it allows us to match the behavior of the atoms that we see with the actual way that the electrons are spinning. Okay, so Hund's rule is in place because we want to recognize that the electrons are doing what they should be doing to give us the magnetic properties that we observe for different elements. Right, so this element is a little bit magnetic because we've got these two electrons spinning in the same direction, creating a magnetic field that's not canceling out. If I go to nitrogen and I put 7 total electrons in, then I find it's even more magnetic because now I have 3 electrons all creating a magnetic field, adding together, increasing the intensity of that magnetic field. So what I find is for elements, the more unpaired electrons they have, the more magnetic the element. Following exactly what Hund's rule predicts. So now I believe Hund's rule. Because when this idea matches with experimental evidence, then I believe the idea. So that's why we follow Hund's rule. That's why we know if we want to show the ground state, we need to recognize that electrons need to be spread out with the same spin in equal energy orbitals before I start pairing them up. If I hit it with just the right amount of energy, though, I can make it non-magnetic. So if I take, for example, back to carbon, if I take this atom and I hit it with just a little bit of energy, I can flip this electron, or I can move it to the next orbital. If I use the right amount of energy, just that amount of energy difference between the ground state and this excited state, I can convert it from a magnetic to a non-magnetic element by pairing up the electrons and giving them the opposite spin. Right, so we can observe the magnetic properties of the substances and use that to match it up with the behavior of the electrons and the spins that they display. So if I'm looking at the ground state, I want to follow Hund's rule. That will give me an electron orbital diagram that matches the actual properties of the elements. And so if I have 3 electrons in the 2p, then I would have a 2p3, giving me 7 total.
What's the difference?
Hund's rule and this guy. Aufbau? Aufbau is just saying that Aufbau dictates what we should do with the electrons when we're putting them in orbitals that have different energies. Right, so Steve's just saying that I need to fill the 2s before I put any electrons in the 2p. Right, so Aufbau says don't do this. If I've got space in the 2s, if I'm trying to give a ground state, I need to fill that up before I put electrons in the 2p because the 2s is lower in energy than the 2p. So I have to put electrons in the lower energy orbitals before I put them in higher energy orbitals. So that's Aufbau. Hund basically says, now what Hund's rule governs a situation where when the lower energy orbitals are already full, and I've got multiple orbitals that are equal in energy. How do I distribute the electrons in equal energy orbitals? And so to make a ground state, I need to spread them out with the same spin before I start pairing them up. So then once they're spread out with the same spin, if I keep putting electrons in, then I start pairing them up. So this last electron I put in here, does it matter which of these three orbitals it goes in? No. Doesn't matter what its spin is. Yes. It has to have a downspin if I've already made upspin for my first three orbitals. Right? Because I can't put them in the same orbital with the same spin. That would be impossible. But it doesn't matter. There's no difference between the 2px, 2py, and 2pz in energy, right? They're all on the same energy level. There's no reason why the new electron has to go in one of those versus the others. But we just do things in the Western world from left to right. So generally you'll see that placed in the leftmost orbital before the next, which is really arbitrary. But now I've got 4 electrons in the 2p, so I have a 2p4. So now we start to see how much more information we get from the orbital diagram versus the electron configuration. The orbital diagram shows me the relative energies. It shows me where all the electrons are. It shows me their spins. It shows me, I see I have one unpaired electron, creating a magnetic field that's not canceled out. So that's going to be slightly magnetic. This doesn't show me that as readily. The electron configuration doesn't really show me the spins. It just shows me how many electrons I have in each of the subshells that's actually occupied. The term paramagnetic refers to an element that is somewhat magnetically attractive. So we'll attract to a magnet. There are degrees of magnetic attraction. So some elements like this with only one unpaired electron won't attract very strongly. So they'll be slightly paramagnetic. There's also a term called ferromagnetic, which refers to elements that can be converted into a magnet. So that's totally different. So here we've only got a few unpaired electrons, 1, 2, or 3, we would call it paramagnetic because it has the ability to be attracted mildly to an electron. The more unpaired electrons it has, the more strongly paramagnetic it would be. The opposite of that is called diamagnetic, and that is illustrated in the context of an element where all the electrons are paired. So of all the elements we looked at so far, up to neon, right? We started with hydrogen, we went over to helium, and then over to neon. The only ones that are diamagnetic or completely unattracted to magnets are the ones where all the electrons have a partner in their orbital. Right? That was helium. And then as we went forward, beryllium, and then neon. There are only 3 in those first 2 rows. Right? And that we can start to see a pattern looking at the periodic table based on that if we extrapolate it. And that pattern is the elements in the second column are all diamagnetic or non-magnetic because these elements have a full S subshell. All their subshells are full, and then the last one that has electrons is an S subshell, and it's also full. Right, so when all the subshells are full, that's going to be a non-magnetic or diamagnetic element. So the elements in column 2, the elements in the last column, the noble gases, because they all have a p subshell that's full. And then these elements here in the last column of the D block, which we'll talk about in a minute, zinc, cadmium, mercury, those elements have a full D subshell. And so only when we have enough electrons to completely fill up a subshell, but not enough electrons to go into a new subshell, that's when we have a diamagnetic element that we're dealing with. So I'll mention more about that in a minute. And then this just shows the order of adding things, right? So right here we only got to the second energy level. Once we go to the third energy level, after we fill the second energy level, after we fill the 2p, we go to the 3s, and we come back around, we go to the 3p. So it's not as simple as saying I'm going to fill up the entire third energy level before I go to the fourth energy level. Because different orbitals within an energy level have different shapes. And the 4s, as we said earlier, is spherical and more compact. than the 3d, although they're very close in energy, and there are situations where electrons might jump from the 3d to the 4s, depending on the situation. We'll talk about one example of that. And then once I fill the 3d, then I go to the 4, and then I hit the 5s before the 4d, again, because of the shape of the orbital. Then as I continue, I hit the 6s before the 4f. That shows you the difference in how elongated the f orbitals are compared to the s. So this order is showing me as I follow it that the 6s, because it's compact, even though it's the 6th energy level, generally electrons will go in there before they go into the 4th energy level, f subshells, because they're so elongated and hold the electrons out kind of far from the nucleus. But once we get to that area of the periodic table, things get weird. And sometimes the ground state will not follow the off-bow principle that we talked about, right? So that principle is basically said, I need to fill up this subshell before I go to the next subshell. There are weird things that happen later on when the energy starts to get really close. And so I'm not going to hold you responsible for any exceptions except two, which we'll talk about a little bit later. So if I ask you to give an orbital diagram or to give an electron configuration, show me where the electrons are in the atom, which orbitals and which subshells and the energy levels they're in, you can follow this. This will give you the answer I'm looking for every time, except with two types of exceptions, which we'll talk about as we go through here. So let's look at an example. So calcium, it's pretty straightforward. With calcium, first thing I need to figure out, that's weird. Very weird. Can't erase it. Okay, whatever. First thing I need to figure out is how many electrons there are. And how do I get that? As we said earlier, I look at the element, figure out how many protons there are, and then I look at the charge and figure out how many electrons there are based on that charge. So if the charge is 0, which most of the examples we're looking at so far are, so I'll probably stick with that on the exam. If the charge is 0, I know the number of electrons is equal to the number of protons. So with 20 electrons, I would start here. So if I'm last for electron configuration, I don't have to draw all the boxes and arrows. I just need to show what subshells the electrons are in. So I would start with the 1s. How many can that hold? 2. Right? So I'm on my way to 20. Then I go to the 2s, following the arrow. 2s, and that can hold also 2, because any s subshell, maximum 1 orbital, maximum 2 electrons. So that's 4 total. Then I continue to the 2p. How many can the 2p hold? 6. So that's 10. I'm halfway there. Got to keep going. Go from the 2p to the 3s. 3s can hold 2. I need 8 more. 3s to 3p. That can hold 6. I need 2 more. 3p to 4s. That's 20 total electrons. I just, count them up and double check it. Make sure I didn't make any mistakes. This question is really not complete. What's wrong with the question? The question gives me this symbol, and it doesn't show a charge, so it's okay. It's safe to assume that it's neutral. That's not really a problem. But the problem is the question doesn't really specify whether I'm looking for a ground state or excited state. So usually the elements are in the ground state. I'm assuming that they're looking for a ground state. But it really should say, right, like it did on the quiz. So if I wanted to draw then the orbital diagram, I could start from this if I wanted. Usually the orbital diagrams are plotted where the energy is increasing, so I have the 1s down here, and then the 2s, and then the 2p, and then the 3s, and then the 3p, then the 4s. But sometimes they're not shown that way. Sometimes they're just all shown from left to right. So you'd have like the 1s, 2s, 2p, 3s, 3p, 4s. If you're drawing the orbital diagram, though, make sure you have a line or a box for every orbital. So if you have a subshell that has 3 orbitals, make sure you have 3 lines or 3 boxes to accommodate those electrons. And people make that mistake sometimes. They'll put too many lines in, and the electrons don't make sense when you're putting the electrons in the atom. So if I've got 20 electrons, I'm filling these up one level before I go to the next, and then I end up with 20 total electrons.